We have gone through the analysis of electric circuits. The analysis was started with the fundamental Kirchhoff's current law and Kirchhoff voltage law. So those particular will be used here as well in the magnetic circuits. We know that when say there is a current carrying conductor, there will be a magnetic field around the conductor. So there is a strong correlation between the electric and the magnetic field. Magnetic field is the coupling media when say we analyze the transformer or say the electrical motors. So beyond this, we will be restricting ourselves to the analysis of flux and the magnetic circuit aspects. Here say this particular magnetic circuit deals with the analysis and application of electric and the magnetic field. The area is not, application area is not restricted to only the electrical machines and transformer, but it is having the application in the radar communication, satellite communication, electromagnetic interference as well. Various devices such as the circuit breaker relays, microwave ovens, etc., they are utilizing the concept of the magnetic circuits. So microwave oven is the appliance which we can easily recognize in our household. Likewise, the starting point is in this is the Ampere circuital law. So we are going to study, as mentioned, the magnetic circuit and the magnetic flux. We will be having an analogy between the electric and the magnetic circuits. The core laws will also be introduced briefly. Now this particular is the famous experiment which I referred in the introduction. So Oersted has observed that there is a magnetic field around the current carrying conductor. So let's say this particular conductor is carrying the current directed upward. So when say we are holding right hand such that the thumb is pointing towards the direction of the current, then the fingers are pointing to the direction of the magnetic flux or field. However, the Ampere has given the mathematical description to find out the magnetic field intensity. So we suggest that the line integral of H, which is the magnetic field intensity around a closed path, is equal to the current enclosed by the path. So this particular definition of a single conductor is extended to a coil or loop. So when say the coil is carrying a current, we are holding the coil such that the fingers are directed towards the direction of the current, then the thumb will be pointing the direction of outward flux. So let's say in this the current is entering, so we will be holding the right hand likewise, so the thumb is pointing directed towards the left. Now these are, you can say, the sum of the structure which we will be using in this particular course. These particular are the magnetic core which are made of the high magnetic permeability material. So this high permeability material, magnetic permeability material is important, and that particular is coming out to be the ferromagnetic material. So the typical range for this ferromagnetic material, the relative permeability value is ranging, you can say, typically between 4,000 to 10,000 likewise. The purpose of this particular the purpose of using the core of high magnetic permeability material is to confine the line of flux within the core. So basically you can say that this particular core is providing a convenient media or path for the lines of flux. Likewise, now when say this particular is of high permeability material, then it is resulting into the increase of the magnetic field strength. So this particular we will be seeing also. Otherwise you can easily recollect that B is equal to mu H. Mu is mu 0 into mu R. So when say mu r value is coming out to be higher, the B is increasing significantly. Another thing, we will be referring to the air gap likewise. So that air gap is having a mu r value is equal to 1. Now there is a leakage flux, there is a fringing effect as well. So how this particular leakage flux has to be understood first. So this particular is a coil which is supplied by a current I, which is resulting into the line of flux. So now not all of the flux lines are confined to the core, but some of the flux lines are linking through the air. So that particular flux lines linking through the air are regarded as the leakage flux. Now unless specified, the leakage flux effect shall be neglected. Now the fringing effect that we have to see, like say this is an air gap. So flux which is flowing in a continuous path. So the total flux at the top will be exactly equal to the bottom. However, the line of fluxes are coming out to be spread within this small air gap area. So this particular spread is resulting into the net increase in the effective area of cross section of the air gap. So usually this area increases by 10% due to fringing. However, unless specified, this shall also be neglected for the calculation. Now here it is a magnetic core where say the same coil having say n number of turns supplied by the current I. So it is resulting into the flux phi. We have neglected the leakage flux etc. and so on. This particular core is having an area of cross section AC, and the material of the core is having a permeability of mu, or you can say mu r. The flux is the flux density multiplied by the area of cross section. So B is related with the magnetic field intensity. So B is equal to mu h. The expression is resulted into likewise H is equal to Ni upon L. So this is the application of the Ampere circuital law. So if you are able to relate the Ampere circuital law, H dot dl, so that is giving rise to the H into L. On the right hand side, it will be the I enclosed. So when say it is having the n number of turns carrying current I, so the current enclosed will be n into I. So this is giving rise to the flux which is rearranged into the form. So it is giving the flux is equal to mmf upon reluctance. So the numerator term is the mmf and the denominator term is the reluctance. So mmf is n into I, where say the reluctance is L upon mu A. Now those particular terms, if you are correlating, you are representing this equation into the equivalent circuit. So this will be the mmf, this is a flux, this is the reluctance. Now what we are seeing, that this is exactly coming out to be the representation of an electric circuit where a resistance is supplied by a voltage source. So that particular is giving rise to the analogy between the magnetic and the electric circuits. So these two circuits are equivalent. When say they are equivalent, you can easily correlate that flux is analogous to the I, this mmf is analogous to the voltage V, reluctance is analogous to the resistance likewise. For further, you have written the expressions like say when say the reluctance is L upon mu A, where say the resistance is L upon sigma A. Sigma is the conductivity, mu is the permeability. So from that particular line you can have the flux is analogous to the current, mmf is analogous to the emf V, reluctance is analogous to the resistance, the reciprocal of the reluctance which is the permeance is analogous to the conductance which is the reciprocal of the resistance. Similarly, you can say the magnetic flux density, that is the flux upon area of cross section. So similarly, there will be a current density J is equal to I upon A. On the analogous line, you keep on elaborating the permeability is analogous to the conductivity. Magnetic field intensity H is equal to, or you can say analogous to the electric field intensity. B is equal to mu H, so J is equal to sigma E. likewise. Now here say we are little deliberating on the effect of air gap in the magnetic circuits. So although say we are making the magnetic core of the ferromagnetic material which is having say the high permeability, but this particular core is experiencing the saturation and the hysteresis effects. So this particular is the hysteresis effect that has been shown. The saturation is coming out to be like this, where say the increase in the current level is not resulting into the increase in the flux level. Now the air gap is introduced likewise. So what we see that because of this air gap introduction, the BH curve is getting slanted slightly likewise. So when say it is slanted, what we will be seeing that for the same value of H, the B value is small. Or you can say for the given value of B, the higher amount of current is needed with the introduction of air gap. So that is giving rise to this air gap introduction is basically resulting into the increase in the saturation current, and that increase in the saturation current means it is help in avoiding the magnetic saturation. That is one aspect. Second aspect, it decreases the inductance likewise. So you can say the slope is reduces, so the inductance value is reducing and the losses are also reduced. So sometimes this air gap is deliberately introduced in the circuit to facilitate these particular objectives. Now when say the air gap is introduced, its reluctance is also participating and the flux is common likewise. So this is represented by a series equivalent where say this particular is the reluctance offered by the core, this particular is the reluctance offered by the air gap. With the same formula you can calculate the two reluctances and the mu r is coming out to be 1 for the air, so that particular is written simply mu 0. Now the point here is that although the air gap length is much smaller, order of only millimeters in comparison to the mean core length which is of order of tens of centimeters likewise, but sometimes the reluctance Rg is coming out to be much predominating because the mu r here is 1 and here say the mu r is of order of 5000, 10,000 likewise. However, when say we are seeing writing the relationship, so this MMF is equal to the flux multiplied by the reluctance of the core plus reluctance of the gap, that particular is then. If you are making a comparison, so simply write supply or source MMF is equal to F1 plus F2, where say the F1, F2 are basically the H into L, H into L. So that is the MMF which we can express with the help of Ampere's law likewise. So when say you are combining it and seeing it as F is equal to F1 plus F2, so this is basically the KVL for the magnetic circuit. In the case of electric circuit, we have seen V is equal to V1 plus V2 because it is already established that phi is analogous to the current, reluctance is analogous to the resistance. So this is a parallel magnetic circuit. So this particular analysis is also on the lines of parallel electric circuit. What we are seeing that this particular is a flux established by this coil is getting divided into the two paths, phi 2 in the central limb and phi 1 in the outer limb. So this particular is represented by the equivalent. So central limb is having say the core, that particular is represented. The outer limb is having a 3-section air gap, this particular is magnetic core segments likewise. So the 3 reluctances are participating. The limb which is on the left side is represented by 1 reluctance because there is no discontinuity as such. So this particular is also having the label like say BAHG, so to identify the section for which the reluctance are marked. Now this phi is getting divided into phi 1 and phi 2, so that particular is the KCL of the magnetic circuits. On this, around this particular, let's say, loop, we can write the KVL relation as explained previously. You can have a closed path. Likewise, you can write the KVL relationship. Similarly, whatever say the MMF across this particular branch, that particular will be the MMF across this parallel branch as well. So these concepts are used in analyzing the circuits. The core loss, it is as say there is a hysteresis nature in the ferromagnetic material, so that is giving rise to the hysteresis loss. Similarly, the eddy current losses are also there in the core. To reduce the eddy current losses, we will be using the laminated core. Laminated core means it is made of thin sheets separated by the insulating material, so to reduce the eddy current losses. Likewise, so eddy currents now confined to the smaller area. Because of that, the resistance offered to the eddy current increases, that is resulting into the reduction in the eddy current losses. This is the mathematical expression for the hysteresis loss. This is the expression for the eddy current loss. Likewise, the total loss are giving as the core loss, which is also regarded sometimes as the iron loss. When say we are working for a coil bound on the magnetic material supplied by an alternating current, so the voltage is related by this particular value 4.44 F and phi n. This we will be having in detailed discussion in the transformer case. So correspondingly the Bm can be obtained. This Bm is substituted, ultimately it is resulting into the expression like pH is proportional to the F to the power 1 minus n into V to the power n. N is the Stevens constant, typical value is 1.6 likewise. So PE, which is the eddy current loss, when substituted, it is coming out to be depending on the voltage square likewise. Now the examples which we are considering in this magnetic circuits, this particular is one source of the magnetic, you can say MMF. This is the another source of MMF because they are carrying the same current of 10 ampere likewise. This is a central limb. So the flux generated by the second, flux generated by the one, that is going through this, and likewise. Here say the permeability is specified, that is 1200. We are given the nature that neglect the leakage and fringing effect, and interested to find out the flux density and magnetic field intensity in the air gap. So this is the equivalent likewise with the help of the available dimension data, area of cross section, various lengths, number of turns in the winding, and the current. We can calculate the MMF, F1 and F2, various reluctances likewise. When say we are applying the KCL, it will be having the nature phi is equal to phi 1 plus phi 2 KVL likewise. So these two equations are solved, which are giving the value of phi 1 is equal to phi 2 likewise, that is calculated. The flux is expressed as the sum of phi 1 plus phi 2. The air gap flux density is calculated phi upon area of cross section. The magnetic field intensity inside the air gap is calculated as V upon mu. So this is, you can say, the calculations are coming out to be simple, where the mu r is specified. Now you can easily see that the air gap reluctance is coming out to be, you can say, comparable or significant in comparison to the reluctance offered by this central limb portion. Although say the air gap was of much smaller value. Now the next, here say in this example we are supposed to work on let the core reluctance is negligible in comparison to the air gap. So this particular is a fair assumption sometimes made to reduce the computational effort or to quickly calculate the value. This we have seen previously that a small air gap is resulting into the reluctance which is comparable or even higher than the core section. So you can say some neglect if specified in the question without much losing the accuracy. So when say the reluctance offered by the core is neglected, this particular will be the equivalent. So corresponding to the air gap length L1 and L2, we will be able to calculate R1 and R2 respectively. Now once that particular is specified, you can easily calculate because the MMF is known. So the flux phi 1, that will be like say MMF upon reluctance 1, flux 2 will be MMF upon reluctance 2, and the supply flux can be calculated as phi 1 plus phi 2 summation. Now once the flux are calculated, you can calculate the flux density likewise. Now this particular is a typical example which has been taken. Here instead of specifying the mu r, the flux is specified, air gap flux is specified, and mu r is not specified. We are also not supposed to make it, you can say, make an assumption where say the reluctance offered by the core is neglected. Here say that has to be counted likewise. So but to facilitate this, we will be making use of this particular BH curve. So purpose of this BH curve is when say the B value is calculated, and if we are interested in finding out the H, make use of this BH curve. Let's say if H is known and we are interested in finding out the B, so the BH curve has to be used. We will be starting with this air gap flux. We will be calculating the flux density. So that flux density will be common in the air gap, that will also be common in the core. Once say the flux density is calculated, correspondingly we can calculate the H from this. So this will be the starting point. The exact steps are likewise. So you have first drawn the equivalent, which is a first prerequisite to attempt the magnetic circuits. These particular, you can say, the dimensions or the information given in the question has been summed up. Now as a starting point, the flux density in the air is calculated. So that particular is given the nomenclature B4, but it is corresponding to the gap. Now with this B4 we can calculate the F4, which is the equivalent MMF across this reluctance offered by the air gap. So this MMF is the H into L. This H is calculated with the help of V upon mu. L dimension is known, so we have calculated the MMF associated with the air gap length. Now this particular flux is common, so the flux density will also be common. So corresponding to the central core, the flux density will be equal to the flux density in the air gap. Now corresponding to, while say making use of the BH curve, we have obtained the H from the BH curve because B is known. So let's say this particular is the 0.8. Correspondingly we have calculated that value is coming out to be 500. Once say H is known, we have multiplied it by the mean core length to result into the MMF associated with that core segment. So total MMF for the central limb in consisting of core length and the air gap is coming out to be 283.66 ampere turn. Now this particular has been coming out to be the same MMF. So this is just like a voltage across these two nodes. This is a parallel arrangement, so the same voltage or MMF will be there. So that particular we can make use of in calculating the H2, which is the magnetic field intensity. So that is equal to the F2 upon L2. It is calculated likewise. We will be making use of the BH curve to find out the value of B. So this is with a green line that has been calculated. It is 0.4 milliweber, 0.4 Weber per meter square. Once a B is known, multiplied by the area of cross section, so the flux is calculated. Phi 2 is known, phi 1 is already given, so we can calculate the value of phi, let's say making use of the KCL for magnetic circuits. Once the flux is known, the area of cross section for the left limb is also known, so we can say we can calculate the B1, that particular is giving rise to the value. Again we will be utilizing the BH curve to find out the value of H, so that is with the blue lines. This particular is coming out to be a 550 ampere turn per meter. So net source MMF will be the MMF across this outer central limb plus the MMF in the central limb, or MMF in the right outer limb likewise. So that particular is calculated. Once the source MMF is known, we can calculate the current needed likewise. So now we can make the summary. Unless specified, neglect the effect of leakage flux and the fringing. The purpose of the air gap is to reduce the net magnetic permeability, reduce the inductance, increase the saturation current level, and thus avoid the magnetic saturation. There is a strong analogy between the resistive electric circuits and the magnetic circuits. So we can make use of this analogy judiciously. This holds true for the series parallel combinations, even say the KCL and KVL for electric circuits are analogous to the KCL KVL for the magnetic circuits. Next, we will be dealing with the mutually coupled inductors and the inductance calculations. For further reading, you can refer these textbooks. Thank you.